So today we're going to begin our discussion of crystal field theory to try to understand relative orderings of d orbitals in transition metal coordination compounds. So crystal field theory began basically from solid state physics, where they were concerned about sort of energy levels in crystals, and ultimately this got adopted originally by inorganic chemists to try to understand relative orderings of d orbitals in actual transition metal complexes themselves. So as Harry Gray likes to say, the physicists took away our molecular orbitals, and then ligand field theory, which we'll discuss later in the chapter, will put them back in. But you can get a good qualitative picture of a lot of the d orbital energetics from understanding this concept. So it starts with the idea that the attractions between a central atom or ion and the corresponding ligands are completely or electrostatic in nature, which, as you can imagine, much like many of the other things we've used in chemistry, like valence bond theory, it's an incorrect assessment of the situation. But it can actually be used to predict the magnetic and electronic absorption spectra of compounds. So the magnetic properties, as well as the color of transition metal complexes, can actually be deduced from understanding some aspects of crystal field theory. And basically, what is that going to do for us? Well, it's going to give us the d orbital energy levels and the splittings as a result of doing this. So let's kind of deal with how this works. So starting with the octahedral transition metal complex, what the setup of this problem is going to look like is that the metal ion is surrounded by ligands that can be considered point charges. So what's going to happen is there's electrons in the d orbitals on the metal that are negatively charged. And then there are going to be ligands with point charges that are also negatively charged that are on the periphery. And the idea is that the energies of the d orbitals will actually split in energy due to unequal geometric interactions with those corresponding charges. So we're going to kind of play with this in an interesting way. So we're going to start with the degenerate set of the 5 d orbitals in an octahedral field of negative point charges from the ligands. And then the electrons in the d orbitals will be repelled by the negative charges of those ligands. And then, of course, that's going to then result in a splitting of these d orbital energies. So let's take a look at what this actually looks like. So the exercise, if we were in class, I would have you draw this out independently, but it's done for you here. So you want to draw the 5 d orbitals on the octahedral field axis system as shown here. So x and y are in the plane, and then z is going above and below the plane. So x and y are the equatorial plane, and then the z-axis is the axial positions. And then what we're going to do is kind of figure out what orbitals are going to go up in energy and what orbitals might go down in energy as a result of all of these sort of negative point charges that are then interacting with the d orbitals along those particular axes. And if you remember, these are really the sigma bonding axes in an octahedral compound. So all the bonding is going to take place along x, along y, and along z. And then we're going to figure out what actually is going to happen as a result of this interaction. So if we move forward and superimpose the d orbitals on that axis system, what you'll immediately see is, and I'm giving you from group theory, I'm giving you also the symmetries of those d orbitals. So there's a doubly degenerate set of d orbitals, which is Eg, and those are actually going to be the sigma bonding orbitals, as you'll see throughout the rest of our discussion with transition metal complexes. So dz squared lies completely along the z-axis. And then x squared minus y squared lies completely along the x and y axes. So these are effectively, directly interacting strongly with the ligands that are coming in to basically make sigma bonds. So that's going to be really critical. So that's going to be sort of synonymous with the EG orbital set. Then the T2G set, as you'll recognize, that's DYZ, DXZ, and DYZ. Should put that as XZ. Sorry about that. But in essence, what you're looking at here is all of these orbitals actually point in between all of those sigma bonding axes. And if you sort of remember, sort of just the nature of how these things are playing out, these actually have pi symmetry. And because they have pi symmetry, they're sort of pointing in between the regions of where you actually get sigma bonds formed. So those are going to have less repulsion with respect to these guys here, which have significantly more repulsion because they're directed along the bonding axes or along the sigma bonding axes. And to sort of finish this picture, the net result of this is that the T2G set, which is here, remember, these are much smaller interactions, so they're repulsed less. So those actually come down in energy with respect to if you had a uniform series of point charges surrounding the transition metal complex. So these get reduced in energy with respect to the starting point by basically 2.5 times the actual splitting of this entire d orbital set. I'll explain what that is in a minute. And then the more repulsed orbitals are the EG set, and that's because, again, they're directed along the bonding axes. So those get repulsed in an octahedral crystal field, and those get raised up in energy as a net result of it, and they're raised up by an amount that's 3/5 del zero, or del, sorry, it's not del zero, it's del O, O for octahedral. And instead of saying delta, we just call it is delta O, but we call it del O for short. And del O, as you can see, is this splitting that you see here between the T2G and the EG sets. And that's actually known as the octahedral crystal field stabilization energy. Shorthand is TFSE. But this is also known as the ligand field stabilization energy, and I prefer that terminology because that's what we use in the textbook at the present time. And really what you're doing is, if you sort of see what's going to happen, is down in the T2G set, you can have a maximum of 6 electrons. And you'll see that, oh, the 6 electrons that are down here, and that means there's 4 possible electrons that can go into the EG set. And then you can kind of gather exactly what is going on here. So we have 10 total electrons, but the other way to think about it is there's 3 orbitals here, and then there's 2 orbitals here. And then you can kind of get from that, that's the energy separations to basically make sure that we are conserving energy. If you come down with 3 orbitals, that's going to be 2/5 del O. And then if you go up in energy with 2 orbitals, that's going to be 3/5 del O to maintain conservation of energy with respect to the starting point of that spherical crystal field. So this is the beginning of the problem, and then you can kind of see that in an octahedral field of ligands, where there's 6 ligands approaching this metal complex, or to make the metal complex along the X, Y, and Z axes, the T2G orbitals are actually stabilized, and then the EG orbitals are actually destabilized. And that's going to really be the quintessential lesson for understanding that if you base everything on solely electrostatic repulsion, you will get this energy splitting, and then this energy splitting is then going to dictate the color of the molecule and the magnetic properties of the molecule, because that energy separation is going to determine how the d orbitals are actually filled. and if the electrons prefer to fill these 3 orbitals or if they prefer to spread out among all 5. And that's a good place to stop before I touch on the next topic. So I will see you in a little while, and thank you.